You, me, we all age starting from our 30s. We notice that our skin becomes less elastic and it becomes harder for our body to rejuvenate itself. But why do we age? Why does it all go downhill after your 30s? In order to understand why we age, we have to take a look at the concepts and processes that aging involves. So what is aging? Aging is the loss of efficiency of tissue renewal. In order to maintain tissue, the cells of your body have to divide. Within 7 years, all your cells are replaced by new ones. It's like you're completely reborn after 7 years. The process of renewal of cells involves the duplication of genetic information, which is encoded within the DNA stored in the nucleus of the cell. So renewal of cells means replication of DNA. It's very important that DNA is protected against degradation, to ensure there will be no loss of genetic information. But a fact is, with every cell cycle, the ends of DNA will shorten, due to a mechanism within the replication system. This loss of sequence signs the cell to stop replicating itself. In order to protect the genetic information within DNA, the DNA is elongated with non-informative sequence, named a telomere. You could compare this with the plastic egglet at the end of your shoelace. The shoelace is the coding DNA, and the plastic tip is an extension that protects the integrity of the shoelace, causing it not to unravel. Within the cell, the telomeres are elongated by an enzyme, telomerase. Telomerase acts as a mold to elongate the telomeres of DNA. When degradation does take place at the end of DNA strands, telomerase renews the protective telomeres to ensure the informative coding is still safe, so that normal replication can take place. After your 30s, the telomere protection is not sufficient, and the chance of DNA loss and thus loss of genetic information increases, resulting in less efficient cell renewal, which means loss of tissue integrity. And this phenomenon plays a crucial part in what we call aging. So, short recap. After multiple divisions of cells, the DNA shortens and lead to aging. But if we take a look at cancer, a highly dividing cell that doesn't seem to age, this seems to go against the principle of aging. How is that possible? Studies have shown that cancer cells have a higher telomerase activity than healthy cells. So cancer cells do not age, and this seems to be due to a higher telomerase activity. Is telomerase activity the key to reverse the ticking clock of your life? And is it possible to crank up the telomerase activity in healthy cells to stay forever young? We want telomore.